אחלה, טוב, תודה רבה, introduction. טוב, אז אני אדבר איתכם קצת על תלת מימד, ובאמת איך אנחנו יכולים להשתמש במודלי foundation models ומולטימודליים, כדי באמת לגנרט ולהבין בתלת מימד. אני אדבר קצת באנגלית, אבל תרגישו חופשי לשאול שאלות גם במהלך ההרצאה, גם בעברית. אז נתחיל. Okay, so we have seen many, so I'm sure you've seen all kinds of foundation models so far, and kind of a general pipeline for training these multimodal foundation models is that you collect a huge amount of data. So let's say you have this huge data collection of 2D images, then you train your machine learning model in some self-supervised way, and then once you trained it, you kind of apply it to many downstream tasks during inference. And that works really well in the 2D domain. So for example, I'm sure you've already seen discriminative models like CLIP, which map images and text to the same representation. You have models like segment anything that can also segment objects in 2D. DINO or DINO v2 models that kind of produce very useful representations for which you can apply different tasks like semantic segmentation and matching. And you also, of course, 2D generative models, which, I think the last time I kind of wrote this presentation, Sora was the best, but I'm sure yesterday came a new model and probably beat that model already. And that's great. So we have very good 2D models to perform all these tasks. But the question is, what about 3D? Well, can we simply perform the same sort of pipeline in 3D? And just to tell you an idea of what we're interested in doing for 3D generation and understanding, we can do things like, for example, using a text or a click. You might want to select or describe an object in a video, and then we want to kind of track all the objects that correspond to that object in 3D. We may want to segment objects either using generate objects or scene from text. Or produce multiple views of a given scene, as well as dynamics or deformations and so on, and generally physics, interactions, imagine generating flowing water in 3D and so on. So can we just apply the same kind of pipeline of just training very large model using a huge amount of data and just then applying this on a bunch of inference tasks? Well, the problem is that unlike 2D, in 3D, we have a much smaller data collection, especially with respect to the dimension of the data, which could also include deformations, large scenes, very compositional scenes, and so forth. So that kind of pipeline doesn't work very well, okay? So what about 3D? What I want to kind of convince you in this talk that we can simply distill 2D foundation models multimodal ones in order to perform all these interesting 3D tasks. And the way it works is by a pipeline called neural rendering. So you start with 3D model. That's the 3D representation that you want to learn. And this is where you kind of have the control. You can design a kind of a representation which encodes some general physical priors about the world. So for example, it could be multi-view consistency, like a nerve model. It could be the ability to control materials, the roughness of objects, and so on. And it could be maybe elasticity and other physical properties. So you have this model, and then what you're going to do is you're going to apply it through a differential render. So you can think of it just like taking a photo of your 3D model in a differentiable way, producing observations, and then sort of matching them to ground truth observations, and then kind of back propagating the reconstruction loss back into the 3D model. And that works really well for kind of all kind of scenes and so on. But the problem is that we're still stuck with this issue that we still need multi-view data in this case, limited 3D data. So what we can do instead is simply replace this kind of reconstruction loss with a prior of a 2D foundational, pre-trained 2D multimodal foundation model, okay? And so, of course, this can be discriminative or generative, can be conditioned on text or whatever it is that you like. But now we have kind of lots of observations with which we can train these models, and we're going to see how this is useful for 3D generation. So if you remember anything from this talk, is this slide, We have a 3D model, and what we want to do is we want to use 2D foundation models in order to train our pre-trained ones. So let's first talk about 3D generation and editing. And so I'm going to start with kind of earlier in this journey, back in 2022, where what we were interested in is kind of stylizing objects. So we start with an input mesh, and we have some text, and we want to produce matching stylization of that mesh, you given the text. And sort of the general pipeline is as follows. You have a mesh, you apply, what you learn is a neural network or the neural style field to produce a stylization of the mesh. And kind of briefly speaking, you take any input coordinate, you pass it through an MLP, which predicts a color and a displacement. And then you apply this color and displacement for each point of the mesh. And this gives you the stylization. So more specifically, you color that point and you displace it distance d along the norm. So now you have the desired stylization. The next stage is to kind of differentially render it to a bunch of 2D observations from a bunch of views. And what you want to do next is compare it to the input text that you want your stylization to match. So for this, we're going to use here's our first example of foundation model that we're going to use, and that's called CLIP. And basically, I'm sure you already know what it is. It's going to encode images and text that are close to each other to a similar representation, and those that are dissimilar to presentation, which is far from each other in a cosine similarity. So what we're going to do is we're going to use this, basically. We're going to apply those renderings into an image encoder, get some representation, and similar with the text, we're going to take the similarity, and this is going to be the objective with which we're going to supervise our neural style field. Great, and this works really well. We can sort of stylize a bunch of meshes like the Iron Man, colorful crochet candle, brick lamp, and even out of the main objects like the astronaut horse. Great. But the thing is, okay, so this is really an example of that pipeline I told you before, where you have a 3D model. What did we have now? We have an input mesh that was frozen. We have a learnable style, okay? And we have the foundation model that we use is CLIP in this case, okay? And we also extended it to the dynamic setting where we wanted to stylize dynamic deformable objects using text like you see here. That's great, but what if we're interested not just in stylizing objects, we want to produce full objects, full 3D objects? Then one of the seminal works in this field is called score distillation sum. And the idea is as follows. You start with your 3D representation. For those of you who know, that could be a nerve or 3D Gaussian splatting. You render a given view from that 3D scene. Then what you do is you apply a bunch of Gaussian noise into each of those, into this rendered view. You get a bunch of kind of noisy images, x1 to xn. And then what you're going to do is you're going to take a pre-trained text-to-image model, and that is going to be a diffusion model. So just to briefly kind of refresh your mind, what does diffusion model do? It tries to kind of, given a noisy image, it will try to sort of predict the noise and sort of denoise images at multiple steps. And so, and it does so for training images that are in the distribution. So we're going to use exactly that fact, and we're going to ask it to reconstruct the noise with which we added to the images. And the idea is that if it's going to be good at reconstructing the noise, then this rendered view is probably within the distribution of images that this text-to-image model was trained on. Okay, so then we're going to use a reconstruction loss, and this is going to be backpropagated into the model. That's great, but the thing is, not all the noises are created equal. So for example, if I were to take epsilon1, apply some noise, and I'm going to denoise it, maybe that gives me a good image. So for example, an image which is photorealistic, matches the input text, and so on. But maybe the last image is not so good. You know, maybe it's kind of not so photorealistic, doesn't match the input text, and so on. So the idea is what we want to do is really we want to kind of reweight the kind of contribution of each noise into the loss. And the way we're going to do it is you're using some sort of a reward model. Basically, the reward model could be some way in which we take those generated images and give score for each of those images, how much we want to use it for our loss. So for example, what could that reward model be? It could be a clip model that just gives you a score, how similar the image is to the text. But could be many other things, such as a VLM, question answering reward, an aesthetic reward, or even a human reward from examples like RLX Chef and so on. Okay, so so let's go back. We have those noisy images. We're going to kind of get scores for each of those noisy images using our reward model. And what we're going to do is we're going to now sort of kind of use these scores to produce a weight for each of those reconstruction losses for each of the noises. So for example, let's say we have a noisy example that ended up producing a bad image according to my reward model. I would want to weight it down in my loss. But maybe I have a good example, then I want to give it a positive weight, a higher weight in my loss. And that's where the reward weighted score distillation sampling is coming from. And I can then back propagate it again, just like score distillation sampling. Okay. And that works pretty well. So here you can see a bunch of examples. It works particularly well in compositional examples. So here you can see the state-of-the-art baseline, where you kind of give it a prompt with a man with a bird wearing a suit, holding a pink briefcase. And now this sort of fails, but our example is able to capture the briefcase. It can also capture better fine-grained details. Here's another compositional example where you can sort of depict the brown bag better. And here's another example demonstrating the compositionality aspect. So the cat is not inside the cheesecake, but beside it. Okay? And you can choose your favorite reward model as well. So for example, you can see an example of, let's say, the mini Chinatown, where we chose the aesthetic reward, something that kind of reward us for being aesthetic. Then it decided to add those bushes because it thought that that's a more aesthetic thing to do. The nice thing is this method is like a plug and play method. So you can, there's different work in the past that used SDS not only for 3D generation, but for editing. So we simply applied our approach there as well. And we kind of get an improvement in editing as well. So you can see, given a text like a white lion, I want to change it to a white wolf, and that results in a better editing output. Okay. Any questions so far? Or I'll continue. Okay, so so now we talked about, so let's go back to that pipeline, right? We have a 3D model, we have a sort of pre-trained foundation model, and now we kind of train the full 3D object. And what we used to train it is a text-to-image model plus a reward model for that, okay? So we talked about 3D generation and editing, and now I want to show you that this pipeline also is applicable for 3D understanding. So recall, what are we interested in 3D understanding? We want maybe to segment a 3D scene, maybe we want to track points and so on. But I'm going to demonstrate it on one particular task. In particular, what we have is we imagine that we have an input monocular video, like this image of a person breaking a cookie. And what we want is, given a click or a text describing the object, we want to segment the object, and we want to be able to render the original video where we either sort of fix the camera view, and have a changing time steps like the original video, or we can sort of even fix the time step and just change the camera view. Okay, so you can see here that the cookie and the hands sort of are fixed in time. We're not moving them, and we want to do that using sort of user instruction, which could be a text or a user click. So the general pipeline stays the same. We still have a 3D model, we still have a foundation model, but now we're just going to change the 3D model to be a semantic one, semantic 3D model. Okay, what does that mean? Specifically, we're going to use a dynamic 3D Gaussian model. Doesn't matter if you don't know what it is, but just for those of you who know, like I can say it, where we have also appearance and semantic features as part of the model. Okay, so more specifically, we're going to start with a bunch of 3D Gaussians that are representing the 3D scene. These are going to have spatial parameters like location, rotation, and scale. as well as appearance properties like color and density. We also want to be able to deform them in time. So we have a representation of the 3D at any given time, any given moment. So we're going to have a deformer that's going to take each of the Gaussians and going to sort of produce deltas in location, rotation, and scales. And now what we're going to do is we're going to sort of splat them into the image space. So that's kind of the rendering part that takes my 3D representation and produces an observation. So remember, we start with a video, so we can do this for every time step, and we can compare our rendered image into the ground truth view that we have from the video. And that's going to give us one of the losses. But crucially, what we're going to do is we're going to add for each Gaussian a semantic feature F, okay? And the way we're going to learn this is the same way as we did splatting for images, but now we can splat semantic feature maps, okay? So what we're now going to do is we're going to take a ground truth observation, pass it through a model called like CLIP or DINO and so on, produce a reference feature map, and then compare it to a rendered feature map, okay? So now what this is going to give us is going to give us a 3D representation where each Gaussian also has a feature representation. So, and again, this follows the same pipeline that we saw before. We have a model, then we have a differential renderer, and finally we are matching what we render with some sort of a foundation model. So how do we, once we have those features in 3D space, how do we go about segmenting them? So recall we have a model like CLIP, for example, where we can match images and text. So now what we can do is replace the image with lifted 3D features. So each of the 3D features I can compare with the feature of text, okay? And if it's above a certain similarity threshold in porcelain representation space, then I can say that's the object. Otherwise, it's not segmented as the object, okay? So you can see here different examples. This is for user click, but we also have examples for using text. And the thing is, really, you can choose your favorite kind of foundation model for this. So you can use DINO, you can use combine it with LSEG or even SAM for this. And you can increase the granularity. So let's say you click on the fingers, you might want to segment the fingers, but as you kind of reduce the threshold for the similarity with the features, you can now also segment the hands. And the thing is, this is all real time, right? So you can select a different, once you train the model, you can select a different object, click it, segment it as well, and sort of, or use text for that. So this is all real time. Great. So what did we see so far? We saw how we have this 3D model, and we train it using some sort of a pre-trained 2D foundation model. But one question we ask ourselves is, can we do the other way around? Can we actually use the 3D model to improve the foundation model itself? So going back, if you like. So instead of this direction, where we kind of use the foundation model to train a 3D model, we want to kind of reverse the arrows, right? So it turns out that the model I just described, if you take your original DINO features and you re-render them exactly in the same position, then they're much cleaner. They're now 3D consistent. And so you can think of the model as sort of denoising these features or removing any inconsistency that we had at the beginning. So these are PCA of the rendered features compared to the original features that you started with. So now what you can do is you can take your re-rendered features, which are 3D consistent, and simply fine-tune your foundation model with these features, and you're going to get a much more 3D consistent model. Great. So how much time do I have? Maybe 10 minutes. Okay, so far we talked about 3D, and that's great. But I also want to convince you the whole pipeline is not just applicable for 3D, but other modalities. So this is a multimodal day, so hopefully you're going to see other modalities as well. And I'm going to show you this in the video modality, okay? So what did we have? We have a 3D model, and we had a way of rendering it to 2D observations and using 2D foundation model. But what if we just replace the 3D model with some sort of an expert model, and we have a way to map the output of that expert to some pre-trained foundation model? And specifically, we looked at it in the context of audio to video generation. So you start with this, your text to image or text to video model. And, you can imagine the general pipeline is that you have a text, you encode it into tokens, and these are passed into the pre-trained generator. And let's say we have our expert, which is kind of an encoder of audio into audio tokens. And now the only thing you need to do is kind of map those audio tokens into textual tokens. So again, with a little bit more details, you have your video generator, like you see here. And now you have your input audio. You begin by sort of dividing it into different chunks. You then encoding it and mapping it into pseudo-textual tokens. And then you construct your input to the video generator with these tokens. Okay, and you do this in a coarse-to-fine manner. So you choose the tokens to depict the local audio region that you're at, but also have a global context of the entire video. And this is what you pass to as textual tokens. You pass this to your video generator. And this works. So here you can see examples. Now, of course, with current, if this is a plug and play method. So if you now take the newest kind of text to video generators, I'm sure you're going to get even higher quality than this. The nice thing is that since we have a joint audio plus text representation, right? We mapped audio tokens to textual tokens. We can combine the two. So we can have a video of some temporal tokens with some vibrant red orange foliage. And this is what you're going to get. And here is the same audio, but on the moon. Okay. So you're going to get. Great. Cool. So kind of last example, I'm hoping I have enough time. So this was an example here. What was the expert was the audio encoder. We have a way of kind of mapping between the audio tokens to textual tokens. And we finally have our text to video model, right? Last example is where we kind of want to use a generative mapper instead. So imagine that you have your pre-trained generator, but this time it maps a sequence of masks or mask inputs into a video. And what we're going to do is we're going to kind of learn in a generative way to map text and image into a set of mask trajectories. So just to give you an illustration of this, we have a text and an image. We're going to map it to a set of masks that are temporal in time. And then we're going to take these masks and we're going to map them into the final video output. Okay. So again, what's the expert knowledge? If you like the clip, text encoder, and image encoder, we have in a generative way, we kind of map between text and mask trajectories. And finally, we have a way of mapping mask trajectories to the video output. So let's look at the first stage, the image to motion mapper. That's basically kind of mapping a very standard diffusion model where you simply concatenate the input image and you kind of use standard gross attention with the text. We extract what's called a motion prompt, but that's something pretty standard. And then we generate this sequence of masks through time. And now in the second stage, we have this sequence of masks and we have those, and we concatenate them to the input noisy images, a noisy video if you like, and we apply, we do standard diffusion model where we denoise the video. But now because we have those masks, we can do two special things, okay? Specifically, the way we're going to attend when we do kind of the architecture itself contains both contains both self-attention and cross-attention layers. For the self-attention, because we have masks, what we can do is, for example, the dog and the cat, we can ask the model only to self-attend within the mask regions. Okay, so within the dog or within the cat. When we have cross-attention, so for example, from a given text that describes the dog or the cat, we can also ask it to the text to cross-attend only to the regions that correspond to the dog or to the cat, okay? And this actually works pretty well. So here you can see a bunch of examples for our model in comparison to baseline. Here's another example. And generally, what we see is that much better object specific motion accuracy and consistency. And here you can see also an example of orangutan where the baseline is unable to produce the correct motion. Okay, so here are a few more examples. I'm going to go quickly to the kind of questions. Great. So what's the conclusion? So we have this pipeline, right, where we have a 3D model and we have a pre-trained foundation model. We saw how we can use the foundation models could be discriminative or generative. We saw how we can apply it for 3D generation, either stylization using clip or object generation using a text-to-image plus reward model. For 3D understanding, we looked at 3D dynamic segmentation via DINO or clip model. We also saw that briefly I talked about the other way around, so how you can improve the foundation model using 3D model itself. And lastly, we talked about video generation. Lastly, I showed that this is a more general concept, can also apply for other modalities like video. So kind of what I want to say is that if you have lots of data, like we saw at the beginning, like in the 2D case, go ahead and train your foundation model. But otherwise, it's very useful to adapt or distill foundation models that have very strong power already, either clip or and so on. And this is especially true if your expert model, your 3D model, has very good prior, okay, about the word. There's a question, can we use this framework for other inverse problems, not just 3D using 2D, other modalities? And generally, we ask the question of when is it useful to do this kind of modular training where you kind of train a model and then you kind of train other models in a modular way versus this end-to-end training.